This video will cover secondary or intermolecular bonding. There are two main types of bonding: primary or intramolecular bonding, which is bonding between atoms or ions within a molecule. The types of primary bonds are metallic, ionic, covalent molecular, and covalent network. The other main type of bonding are secondary or intermolecular bonds, which are bonding between covalent molecules. So these include hydrogen bonds, dipole-dipole bonds, and dispersion forces. The four main types of primary bonding are all very strong compared to these secondary bonds, and as such the secondary bonds are usually referred to as interactions as opposed to bonds. The type of primary bond is generally determined by the element the substance is composed of. For example, a metallic substance is just composed of a metal element, this blue section in the periodic table. A covalent substance is just composed of a non-metal element, this yellow section of the periodic table. And an ionic compound is a metal and a non-metal element, for example, sodium chloride. Now this is a general rule, but there are some exceptions. Covalent bonding occurs generally between non-metal elements. These elements have 4, 5, 6 or 7 electrons in their valence shell, and therefore they need to share electrons in order to gain a complete valence shell. Covalent bonding forms molecules, which are a small group of atoms held together by covalent bonds. These covalent bonds are very strong because of the electrostatic attraction between the positive nucleus and the negative electrons. Covalent molecules tend to be gases, liquids, or low melting point solids. Therefore, they are substances that typically have low melting and boiling points. Now, even though they have strong primary covalent bonds within the molecule, the secondary interactions between molecules are very weak. No primary covalent bonds, the ones within the atom or within the molecule, are broken in order to melt or boil a molecular substance. It's these interactions here, the secondary interactions, that dictate the melting and boiling points. The polarity of a covalent molecule determines the type of secondary or intermolecular interaction between the molecule. There are three main types of secondary interactions or intermolecular forces. There are hydrogen bonds between polar molecules that contain nitrogen, oxygen, or fluorine bonded to a hydrogen. These are the strongest interactions. The next ones are dipole-dipole interactions. These are between polar molecules. And the last one are dispersion forces, which are between non-polar molecules, and these are the weakest. The first type of secondary interaction that we'll look at are dispersion forces. These are often called van der Waals forces and are between non-polar molecules. So electrons in non-polar molecules are usually evenly distributed. At a particular point in time, the electrons may be unevenly distributed and a temporary dipole is formed. Now, a dipole just means a separation in charge within the molecule, and it's represented by these delta minus and delta plus signs. Delta just meaning a partial charge, not a full charge like an ion. Now, this dipole brings about an induced dipole on an adjacent molecule. For example, if these two molecules come into contact with each other, the dipole on the first molecule, the temporary dipole, induces a dipole on the next door molecule. So if the delta positive sign is on this side of the molecule, the delta negative part of the dipole will be on this other molecule here. All molecules have dispersion forces between them, no matter their polarity. So you could have a molecule that underwent hydrogen bonding, but it would also have dispersion forces. The strength of the dispersion force increases with increasing molecular mass. If you have a look at this series here of simple alkanes, as you go from methane that has 1 carbon atom to butane that has 4 carbon atoms, the boiling point increases from negative 161.5 degrees to negative 0.5 degrees Celsius. This is because as you get a larger molecule, there are more electrons in the molecule. Therefore, there will be a stronger dispersion force and the molecule will have a higher melting or boiling point. The next type of secondary bond is a dipole-dipole interaction. These occur between polar molecules that have permanent dipoles. The partial positive charge of one end of one molecule is attracted to the partial negative charge of the other end of the molecule. The strength of this dipole-dipole interaction increases with increasing polarity, so the difference in electronegativity between the two atoms, and it also increases with molecular mass. The last type of secondary bond is a hydrogen bond. Now these are really just a special case of a dipole-dipole interaction where the molecule must contain a nitrogen-hydrogen, oxygen-hydrogen, or fluorine-hydrogen bond. There is a really large difference in electronegativity between the hydrogen atom and a nitrogen, oxygen, or fluorine atom. This causes a very large dipole within the molecule and therefore a very strong interaction between the molecules. The type of secondary bonding a molecule undergoes dictates the melting and boiling points of that molecule. So for a molecule to go from a solid to a liquid, i.e. melt, and then a liquid to a gas, i.e. boil, there needs to be some sort of input of energy or heat to disrupt the secondary bonding or forces or interactions between these molecules. Now, stronger secondary bonding means that more energy has to be required to do this, to disrupt those forces, and therefore the molecule will have a higher melting or boiling point. So as you can see here, fluorine has a very low boiling point, and that's because it undergoes dispersion forces, the weakest of the secondary bonds. If you compare this to hydrogen chloride, it has a higher boiling point because it undergoes dipole-dipole interactions. And then compare this to water, which has a really high boiling point because it undergoes the strongest secondary bond, which is hydrogen bonding. As mentioned previously, all molecules undergo dispersion forces. Therefore, a molecule could undergo dipole-dipole interactions and dispersion forces, or hydrogen bonding and dispersion forces. An example of this are alcohols, which contain this OH functional group, the hydroxy functional group. Now, from the data table below, you can see as we progress from methanol, which has one carbon atom in its chain, to hexanol, which has 6 carbon atoms in its chain, the boiling point increases from 65 degrees Celsius to 156 degrees Celsius. Now, all of these molecules only have one hydroxy group. Therefore, the thing that is responsible for increasing these boiling points are the dispersion forces. This is because as you have a larger molecule, there will be more electrons in the molecule, so therefore it will undergo a stronger dispersion force. This means that more energy is required to disrupt these dispersion forces between the molecules, and you'll result in a higher melting or boiling point.